Hello, this is going to be a brief talk about electromagnetic acoustic transducers, otherwise known as EMATs. We're going to describe some of the basics behind EMATs, how they work and some of the applications that they can be used in. This presentation is a joint venture between Sonemat and the University of Warwick Department of Physics Ultrasound Group. We'd like to acknowledge two organisations that have helped bring EMATs to the state that they're in currently. Firstly, the Ultrasound Group in the Department of Physics at the University of Warwick, where much of the original research for the EMATs that Sonemat currently exploits were originally developed. Secondly, the Engineering and Physical Science Research Council, who funded EMAT research at the University of Warwick for the past 20 years. This is a list of recommended references. The first three are books. The list of names at the bottom of the slide are authors who've made several important journal publications in this area. As an overview of the talk, we're going to start by describing some of the ways that EMATs actually generate or detect sound on samples. We're going to go through some applications, and then we're lastly going to have a brief summary. This video is not intended to be a detailed theoretical treatment of the operation of EMATs. So, why should we use non-contact ultrasound? The first one is obvious, it's coupling free. Something that doesn't always occur to people is that EMATs operate very effectively on curved surface. They're extremely tolerant to misalignment on the curved surface. This tolerance to misalignment really comes about because there is no refraction. The way that sound is generated using an EMAT is that there is an electromagnetic wave between the transducer and the sample surface. There is no sound wave travelling between the transducer and the sample surface. Therefore, we don't get refraction problems. Having a non-contact transducer makes it much easier to inspect moving or hot components. EMATs can be water-cooled and have been operated to temperatures of over 1000 degrees centigrade. Combining all these features together means that EMATs are highly suited to automation or robotic inspection. Also, because an EMAT is not actually physically touching the system in many cases, it doesn't significantly affect the measurement that's being made. When we talk about ultrasonic generation or indeed detection using EMATs, there are three key forces that we need to consider. These are three physical mechanisms by which an EMAT will detect or generate ultrasound. The first is the Lorentz force. This is a force that operates when the sample is an electrical ductor, i.e. most metals. The next effect occurs on magnetic samples, and it's called the magnetization force. Essentially, it's the same as the kind of force that one would get if we held two magnets side by side, either a force of attraction or repulsion. Finally, we're going to mention magnetostrictive forces. These are particularly important for many real-world applications where pipework is operated at high temperature and has a high temperature oxide surface coating. So, samples that we typically consider when we're discussing the Lorentz force are aluminium, titanium, and most types of stainless steel. The reason that stainless steel has an asterisk by it there is because magnetic stainless steel does exist, and where that steel is magnetic, it has a potential for other mechanisms such as magnetization or magnetostriction. The magnetization force, well, this is a phenomenon that can occur on magnetic materials such as steel or iron, nickel or duplex steel. The magnetostrictive force takes part on materials that could be conductors or non-conductors. So an example would be magnetite or duplex steel, or some stainless steels that are magnetic in some way and do have a significant magnetostrictive force. Key among these is probably magnetite. Magnetite is a high temperature iron oxide that's typically found on mild steels that have been exposed to high temperatures. It's actually a ferrimagnetic form of iron oxide. Pipework that's been used at high temperatures, quite often under insulation, develops an oxide scale. This is often found on boiler tubes or petrochemical steel tubes. The slide we can see here is a handheld shear wave EMAT being used on a couple of boiler tubes. The pipe on the left has a more black coloured surface layer. The pipe on the right looks a little bit more red to orange. The red or orange colour here is a thin layer of hematite on top of a much thicker magnetite layer. This could be easily removed, and what we would see is an exposed black, shiny, hard oxide layer. Generally, pipes like those on the right of this image will have much thicker magnetite layers under this very thin top surface of hematite. The pipe on the left as shown here may actually have regions where there is very little oxide surface coating. This is something you need to be aware of if ever demonstrating or being demonstrated an EMAT system. The pipe on the right will typically give extremely strong signals because a magnetostrictive force is extremely efficient. The pipe on the left would typically give much lower and much more variable performance. Whenever demonstrating or considering an EMAT system, it's important to consider the samples that you'll actually be testing rather than some samples that somebody wants to demonstrate to you. Magnetoelastic mechanisms are very complex and difficult to predict. They are extremely dependent on material properties, and they vary with frequency, the bias magnetic field or the dynamic magnetic field that comes from a coil inside an EMAT, and the microstructure of the material. In many cases, the experimental data does not exist that would allow you to model the magnetoelastic mechanisms. These are the magnetic, magnetostrictive mechanisms. Generally, the best way to find out how an EMAT will perform is actually just to place it on a sample and see what happens. Some of the typical examples of EMATs are thickness gauging, EMATs being used with other forms of ultrasonic transducers, high temperature measurements, stress measurement, texture measurement, and by that we mean crystallographic grain texture, guided wave inspection, and weld inspection. And we're going to illustrate each one of these with an example. This slide shows a typical floor detector connected to an EMAT adapter box. There's an EMAT in the foreground on a boiler tube. This first generation of adapter box conditions the pulse, provides suitable high gain, low noise amplification, and the whole device is connected back into the floor detector in 2-channel mode. In this way, the floor detector operates as though a normal piezoelectric transducer were connected to it, and you can see on the screen of the floor detector a series of peaks there that indicate the thickness of the sample by measuring the time between the peaks. The next generation of these adapter boxes contains field programmable gate arrays, or FPGAs. This has been a major step forward. The sample that you can see the EMAT sat on in the picture on the left, well, that sample is a weld between a ferromagnetic pipe and an austenitic or non-magnetic pipe. EMATs will generally work much better on magnetic steels and higher conductivity steels. Traditionally, the performance on stainless steels is pretty poor. However, The adapter box with the FPGA system inside is able to do some signal processing that greatly enhances EMAT performance on samples that you wouldn't normally be able to expect. By way of example, the two plots on the right show a traditional adapter box, so this is giving much more enhanced performance than one would usually obtain with a flaw detector alone on stainless steel. And you can see in that top plot it's very difficult to see any signals. However, the FPGA inside the adapter box here enables you to do some averaging inside the box and some signal processing, and then feed that back to the flaw detector. This results in the plot on the bottom right. Here there are a series of nice clear ultrasonic echoes that you can use to do thickness gauging. So the advance here of including the FPGA inside the adapter box enables you to measure sample thicknesses that previously you just wouldn't have been able to do. Another technique that one often uses with EMATs is to combine it with other forms of ultrasonic transducer. In this example, a pulse laser beam might be used to generate a surface wave. That surface wave could travel to a crack. Different frequencies of the surface wave travel to different depths. So not only will the crack reduce the amplitude of the signal, but it will also act like a frequency filter, allowing lower frequencies to pass under more easily. In this slide, we can see a prototype experimental rig that was developed to use a pulse laser beam to generate sound on a hot steel billet that passed under an EMAT sensor that was water cooled and fitted to a sled. The red line you can see down the middle of this plot represents the Rayleigh wave arrival. And what's happening as you look down this plot, the region where the defect passes under the EMAT, you can see there's a clear reduction in the signal, an indication that there's a surface breaking crack. But by looking in more detail at the frequencies that have got under that crack, you're able to say something about the depth of the crack, not just that the crack is there. Laser EMATs have also been used to do weld inspection. The advantages here are that the system is entirely non-contact and it can rapidly scan across a weld, generating many different modes of ultrasound in one go. If we look at an A scan or a time domain signal for one of these laser shots, what we can see is the P wave is a surface skimming longitudinal wave, the LL wave is a longitudinal wave reflected from the back of the weld, the LS is a mode conversion of a longitudinal to shear, the R is a Rayleigh wave, and the SS is a shear wave that's reflected from the back of the sample. And they're all different kinds of combinations and permutations of waves that reflect and mode convert, but they appear as a discrete set of spikes. An operator looking at this signal might have good reason to be worried about how on earth they were going to interpret the signal. Well, actually the key here is to take that data, turn the signal amplitude into a colour-coded map, and plot it side by side as this system is scanned along the weld. On the left you can see a blank plate representing an ideal weld, and we're able to identify what each of those coloured bars equates to there. It's a particular wave arrival. And the areas highlighted in black here, well, they arise because there are deliberate defects placed in the weld. So we can use this as a rapid screening method. We can do some defect sizing. We can also do some defect positioning within the depth of the weld by looking at how each wave mode is affected. This weld that was scanned here was over 30 centimeters long and was done in under 1 minute. In terms of thickness gauging, in addition to using flaw detectors with adapter boxes, you can have bespoke systems where the generator is specifically designed and optimized to interface with an EMAT. This is more of a lab-based system. And in this case, the amplification built into the box, the idealized matching can be placed inside the electronics within the box. And you can see the signal here being shown on an oscilloscope. These systems can also be made battery operated and portable. This example here we've already seen, well, that's the floor detector with an adapter box and an EMAT. We can use this same kind of EMAT to map stress. In a metal plate that's been rolled or cold worked, there are generally slight levels of anisotropy. Anisotropy equates to different elastic properties in different directions. They're very small, but they can have a significant effect on ultrasonic propagation. In this case, if we send a shear wave down through the thickness direction of the sample, that shear wave will split into two polarizations. One is a shear wave that vibrates along the rolling direction of the plate. Another vibrates at 90 degrees. And by looking at the relative velocities of these two plates, we can actually map stress. So if we have a waveform, sometimes we won't be able to see the difference between the two. We can open up this by using a Fourier transform in the frequency domain. So even though you can't see the data in the time domain, in this case because it was a thin metal sheet, you're still able to see differences. The differences between these two signals could correspond to submicron thickness, and then the difference between the spacing on one signal between the two peaks, well, this represents the two shear wave polarizations, and we can use that to measure stress. As an example of a mapping stress, we took a thick aluminium plate, machined out a region of the plate, and in doing so relieved some of the internal stress. This was then refilled with a new weld and then machined flat. So superficially, the plate looked like it had done so originally. This is a common approach for trying to generate stress fields in metal plates. If we scan the metal plate and look at the degree of shear wave velocity difference and plot it in this simplified relative map, we can see a distribution of stress that matches exactly with what one would expect from the theory. The middle region looks noisy. That's because the quality of the weld here was very poor, and as such there was lots of scattering within the weld region itself. This approach is used for measuring stress in rail wheels as well, and is actually written into a particular European standard. Another example that we'll look at now is how we can measure the crystallographic texture of rolled metal sheet. This could be an aluminium or a steel sheet. This is something that typically isn't done online, but it is possible to do so using this type of EMAT technology. The crystallographic texture of a metal sheet is effectively a measure of how random the alignment of the individual grains that form the sheet actually is random. Superficially, it does look random, but very small variations can have significant implications for what happens when you try to do something to this sheet that involves plastic deformation. If the rolling conditions of the sheet weren't right, then when you try to plastically deform the sheet, it can result in sheet tearing or sheet deformation in a way that you weren't expecting. So how we do it here is we have a generation coil on one EMAT and a detection coil on another, and we carefully select a particular kind of wave, a guided wave, to go from the generation to the detection EMAT. Because it's non-contact, we don't significantly affect the system that we're measuring, and we're able to make very accurate velocity measurements. In a practical embodiment of this system, we take two EMATs separated by a fixed metal bar which rotates. If we just move that metal bar out of the way, rotate the EMATs, all the time in that measurement we're sending sound from one to the other. Here's what the actual prototype system looks like. You'll notice there's a slight difference here. There are actually two detection EMATs in this system because that helps us take some kind of normalized measurement. This makes the system much more accurate, but the basic principle of transmitting on one and receiving on another is all that we need to understand to figure out how this works. We can plot a variation of velocity of this particular guided wave as we rotate, and these measurements can be done in a matter of seconds. If you look at the numbers of the change in velocity on the plot on the left, you can see it going from 5505 meters per second to about 5455 meters per second. That's the maximum variation. It's evident in this experimental data that the actual measurement precision is much, much higher than that. We can only achieve this because of the non-contact nature. It's very difficult to generate this type of wave in a controlled way without using an EMAT. Locked within there is quantitative information about the material property, and we can use it to generate figures such as that shown in the right, which are effectively equivalent to a kind of X-ray pole figure, which is what would typically be used in industry. But to take an X-ray pole figure measurement, you'd have to cut up a small sample, use lots of sample preparation, and then do a long exposure experiment on the sample. Total sample preparation time would be several hours. Total experiment time might be over an hour. So the one on the left is the ultrasonic experiment that we can do in under a minute easily. We have to say the depth of information that X-rays can provide is in excess of what ultrasound can deliver, but in many cases the ultrasound tells you as much information as you practically need to know. This is an example of measuring the ultrasonic velocity and how it varies with rolling direction for some metal sheets. In this case, the top dark blue trace, just for comparison, corresponds to a 3.1mm thick trip steel alloy. You can see it looks very different to the other plots shown here, and the other plots shown here on the lower bunch of graphs, well, they all correspond to a 316 stainless steel that's been progressively rolled to different thicknesses. You can see as the steel is rolled how the anisotropy develops. This is useful information. It can tell you whether the processing has led to the right elastic and subsequently plastic properties. So previously we talked about mapping stress. We can also map texture. In this example we just use a shear wave transducer, and again we're measuring the acoustic birefringence. We're not building up a complete picture of the crystallographic texture, but we are building up part of that picture. We've got two of the three parameters that we need to define texture, and quite often it's just as important to know if there's any inhomogeneity. So the 400 and the 420 subscripts on these W parameters, they're effectively a kind of quantitative measurement of a particular parameter that tells you how grains are aligned in this material. In this case, we were just interested in, was the plate homogeneous? And we can see clearly here that the plate is not homogeneous. More recently, there's been a lot of interest in SH or shear horizontal guided waves. These possess some really interesting properties for a number of different applications. An SH guided wave, as shown here, is propagating in the x1 direction, so that's down to the bottom right, but it's oscillating in the x3 direction. And the wave is a guided wave. It exists through the entire thickness of this particular plate. When we consider how SH guided waves travel along a flat plate or perhaps a curved surface, we get a series of curves. These are dispersion curves. They tell us about the phase and the group velocity of those waves along a particular plate or curved structure. The graph on the left is a phase velocity, and the black dotted line corresponds to a particular wavelength of wave that we would generate. And what we can see is, in this case, that particular wavelength intercepts the SH0 and the SH1 at two distinct points. If we were also able to excite waves at the right frequency thickness position, we would generate each one of these waves in turn. And we have some control over how we do that. Frequency thickness is a way that we represent dispersion curves commonly because it means that we're able to quickly consider what would happen for a plate of a particular material regardless of what the thickness of the plate is, because we only need to work out what frequency we want and what the thickness of the plate is to find out where we would sit on these dispersion curves. These are actually relatively simple curves for guided waves. How do we make a guided wave transducer? Well, this SH wave transducer, this is an EMAT design. It's called a periodic permanent magnet array on the bottom left. You can see there's an alternating array of permanent magnets underneath or behind a wire coil. The permanent magnets set up an array of forces that alternate in different directions, both up and down the page as shown here. This results in a force distribution that's rather similar to the graph shown on the right. When we construct transducers for generating SH guided waves, we usually have to completely encase them in a metal housing. We can do this by using a very robust, low electrical conductivity metal in front of the coil, such as perhaps titanium or stainless steel. We'll also usually make the body out of stainless steel or a similar material to make the devices robust. Some of these EMATs operate at depth below the sea. In this example, and the ruler there for scale, we're using EMATs on a thin plate and we're trying to see if we can detect two simulated defects here. The first one is this 1mm diameter drill hole through this plate. The plate thickness is 1.5mm. And the second defect is a gross defect you can see towards the bottom left of this image. It's a slot that's 9mm long and 4mm wide. When we look at the images, the A scans produced by these signals, we can see quite easily the signal that arises as a reflection from the 1mm diameter hole, and of course, as expected, the signal from the slot is enormous relative to that 1mm hole defect signal. One of the really interesting properties about EMATs generating these SH guided waves is that they propagate around corners with very little loss. Not just curved surfaces, but very sharp corners. In this experiment, you can see this is a stainless steel container. One EMAT is positioned on the side of the container, another EMAT is positioned on the base of the container in this case. What's surprising, looking at the A scan, the time domain waveform on the bottom right hand side here, is that the signals travel around these features of this can with relatively little loss. There is very little reflection when an SH guided wave goes around a very sharp corner. However, if there's a defect there, it will reflect a significant amount of the energy. The attraction to this technique is that from one place on a structure, you can send these guided waves around some very complicated shapes and inspect an entire sample without having to move the transducers all the way around the sample. The types of EMATs that we use for SH guided waves can also be used to generate SH bulk waves in much thicker samples. These can operate in a way that's not too dissimilar to a diffraction grating. So at a particular angle between lines of force that are originally in antiphase at the surface, we can get constructive interference. The images here are of a 22mm thick stainless steel welded plate, both the front and the back of the plate. There are a number of deliberate defects manufactured into this plate. Stainless steel welds are notoriously difficult to inspect because the high anisotropy that arises in the welding process steers the ultrasonic beam into directions that make it very difficult to get the sound from the transducer to the weld and then back to the transducer. It's long been hypothesized that an SH angle bulk wave would give high sensitivity. And we believe the paper published in this area is a first demonstration experimentally that taking the best case standard compression wave type inspection, you can't see all the defects in this plate. using the angled SH bulk wave EMATs, it was possible to inspect this plate from any single side of the weld and find all of the defects. This proved to be impossible using alternative ultrasonic methods. The particular setup used was using an emitter and a receiver in a pitch catch geometry scanned along the weld from one side of the weld. And in each case, no matter which side of the weld the EMATs were positioned on or which face, front or back, defects were found in the weld with different levels of signal to noise, but all of the defects in this plate were found using this technique, and they couldn't all be found using conventional ultrasonic transducers. So, let's try and summarise some of the things that we found out about EMATs in this talk. Let's start with the bad news. EMATs are only going to operate on electrically conducting or some types of magnetic sample. This rules out inspecting plastics, for example, or glass, and would actually make inspecting very low electrically conducting materials like carbon fibre composites quite difficult with EMATs. EMATs are undeniably inefficient compared with piezoelectric transducers. They also tend to be a little bit larger than piezoelectric transducers. EMATs need to be close to the sample that's being inspected, typically within 5 mm, but the exact distance depends on the kind of EMAT that's being used and the kind of sample that's being inspected. For example, in some situations it's difficult to get significant signal to noise if the sample has poor electrical conductivity, even with the EMAT in direct contact with the sample. In other cases, such as in some of the high temperature oxide coated pipes, EMAT measurements can be taken at distances of over 12 to 13 mm away from the surface of the pipe. The good news when it comes to EMATs, well, EMATs can generate most of the wave types that piezoelectric transducers can, plus a lot of other different kinds of interesting wave modes without some of the drawbacks. EMATs are non-contact devices, and as such they do lend themselves to automated inspection, inspecting hot or moving components. They can be made in such a way that they're robust and inexpensive. So EMATs are not always the right solution for every situation, but because they offer some very unique advantages, in many cases they should be considered as a way of inspecting a sample or a material. Thank you for your attention. We hope to have given you some insight into some of the ways that EMATs work. We also hope to have given you some thoughts on potential applications that EMATs could be used for. If you have any research questions, please contact the following email address s.m.dixon@warwick.ac.uk for research-based questions. Any questions relating to EMAT equipment, please contact the address given below at Sonemat.